Hey, pleasure. Hello, everyone. Good to see you. That's good. It's a big crowd. It's the biggest crowd we had in a long while. It's also the first Blackboard talk we had in a long while. It's really wonderful. I mean, as a proper talk, not as a discussion. Very good. Thanks for insisting.
I didn't insist, but yeah.
Thanks for suggesting it. Yeah, it's a great pleasure to see you all, and also a great pleasure to see the speaker, Alexander Kliesch from the Technical University of Munich, who's visiting us Monday, Tuesday, Wednesday, and a bit into Thursday.
Yeah, exactly.
Yes, so we will speak about 3 papers that are all connected in one way or the other to near-term quantum computing and the goes and no-goes of quantum approximate optimization, with a slight emphasis on the no-goes, if I get it right.
Yes,
and the goes, but it is what it is. So thanks for coming. It's great to have you, and yeah, I look forward to it.
Thank you for the introduction. Should I close the door, or should I can?
Yeah.
Yes.
That's your speaker, so.
Okay, that's fine. Okay, so welcome everyone. So just like Jens already said, my name is Alexander Kliesch. I'm from TUM. Thank you very much for the invitation. And yeah, it was already some very great 2 days that I've been here. Lots of interesting discussions, and yeah, thanks for having me. And this is a wonderful environment, so very pleased to be here. I just wrote down like these references to the archive of what I will talk about, and basically what I will talk about is what my work on variational quantum algorithms applied to combinatorial optimization problems, which I've looked at during my PhD, which will finish somewhat soonish, I guess. So yeah, and I will basically give you a brief overview over the results and the techniques. As far as I'm aware, not everyone here is working with variational quantum algorithms, or in particular with combinatorial optimization. So I will also give a short introduction to what actually the problem is. Okay, then let me just define very briefly the HowQuaaA ansatz. In particular, for combinatorial optimization. So HowQuaaA basically comes from the field of quantum adiabatic computation, and the goal is basically to adiabatically evolve from the ground state of some Hamiltonian to the ground state of another Hamiltonian. And so in particular in HowQuaaA, these Hamiltonians are called quantum Hamiltonian. And we always assume that this is a local Hamiltonian, and that is in our problems we always talk about graph problems associated with some graph.
When you say local, do you mean K body for some finite K, or do you mean geometric?
No, K body for some finite K. Yes.
The common misunderstanding.
Yes. So all we care about is that it's a sum of Hamiltonians on a bounded number of acting on a bounded number of qubits. Okay, and then we also have the mixing Hamiltonian, HB, and in our case, this is basically the Hamiltonian that we start out with in terms of evolution or adiabatic evolution, and in this case, this is just the transverse field. So we would apply an X on every vertex. Okay, and now, so how does HowQuaaA work? Well, so first of all, we choose the so-called level of HowQuaaA, which is parameterized by some letter number P. And we would choose this, and then the HowQuaaA state would be defined in terms of parameters beta and gamma, which are which are p-dimensional vectors. And the ansatz is basically based on like trotterization of this adiabatic evolution. So depending on how large you chose this p, you would have this alternating application of or implementation of the mixing Hamiltonian and the problem Hamiltonian. And your input state, and that's basically the idea. So you started in the ground state of this mixing Hamiltonian, which is easily preparable, and this is just the O plus state. Okay, and this gives us a state. And yeah, as I've said, data are, well, they are vectors in RP, but you can actually reduce them to the interval from 0 to 2 pi. And so if we have some combinatorial optimization problem, then we would have, so these betas and gammas. So we would choose them in such a way such that the expected value of our problem Hamiltonian under this ansatz state would be optimized, either maximized or minimized. Okay, we would prepare the state, and so this HG comes from some combinatorial optimization problem. We would prepare the state with our quantum device, and then we would measure in the computational basis. And this would give us some solution candidate to our combinatorial optimization problem. Just read out this measurement result. Yes?
I don't really see how it's related to a combinatorial problem.
Yes, this will be the next part. Yeah.
It's the Hamiltonian.
So it's encoded in this Hamiltonian, and I will go into more detail just now. Other questions? Okay, good. I'm gonna stay here. I hope you, if you have any questions, like for references or something.
Is the mixing Hamiltonian generic, or do you assign it to
Good question. So in general, you can choose it differently. Like it doesn't have to be this, and there is actually something which is called the also QAOA, which is called the quantum alternating operator ansatz, where you basically would have some other mixing Hamiltonians. But for the classical QAOA, we will just stick with this one. And in general, like what I just wrote here, I mean, this is like for binary problems, but in fact, in one of our papers, we looked at K coloring, where you have basically K, a problem not binary, but with K levels, and then the answers would be a little bit different, but it would still be the same thing. So
how do you? So you need to choose Q kits to.
Yes, for K coloring, you could, for example.
You don't know K in advance.
You do, like if you, for example, have the max K cut problem, and if your goal is okay to do some, like to find some K cut, then you know the K. Okay. That's okay. Then let's talk a bit about this Hamiltonian. So the main problem that we've talked about, for example, is the max cut problem. So does everyone know here what max cut is? Or okay,
but it doesn't hurt to say it.
Of course, very good. Yeah. So max cut is basically okay. You are given some graph. Let me briefly draw it. And now the goal is to assign either 0 or 1 or one of 2 colors to each vertex here. Like for example, you can do this like this. Yeah, this is basically either coloring or cut that you can. And why does it mean cut? Because the goal is now to maximize the number of edges such that the two vertices joined by this edge are have been assigned different colors. For example, here should be in fact should all have different colors, like here is 0 and here is 1, and this is the this is some solution, and the cut size of this would be now 7. But this is actually not the best possible cut. Like you could see, I think you can achieve a cut size of 10. So next up, G of C would be 10. And this problem is one of the more original NP-complete problems, and therefore we do not expect some to be there some classical efficient algorithm that computes actually this maximum cut. And well,
and the original means like more practically motivated, or
that, and it was also so there were like the first original one was of course like the Cook-Levin like 3 set, and then I think the next ones were by Karp, these 21 NP-complete, and this is one of these. Okay, so we do not expect to find a classical algorithm to solve this. Well, we also somewhat don't expect a quantum algorithm to exactly solve this and efficiently, and therefore, but in general, like what you can do there is, okay, you can say, I want my algorithm to be polynomial time, but it should still output some solution which is very good compared to the actual maximum. And this is called an approximation algorithm. So it's polynomial time. It doesn't give you some, it doesn't guarantee you that you achieve the perfect solution, but it gives you, it should, in best case scenario, give you a very good solution. At that point, you're happy. Okay, and now let's see, okay, what would this Hamiltonian be associated with the max cut problem? And one can relatively easily see that, well, we want to like maximize these to be different. So what we could have here is just like you said in Ising. And right, so this would be the max cut Hamiltonian, and the maximum eigenvalue of this, like we would now associate a cut with like the expectation value of this Hamiltonian under a certain cut would then give you the cut size, and maximizing this eigenvalue would then give you the maximum cut. Okay, and this would be the thing that we plug into the QA. Yeah, so one interesting thing is, so the depth of the QA circuit for this problem scales linearly in both the level P that we're choosing and in the maximum degree of our graph. This can be seen by looking at edge colorings, for example. And then if you look at the QAA ansatz, you could see, okay, you could write this as a product of 2-qubit gates on disjoint supports.
Do you mean that this is an necessary condition to find a good solution?
This here?
Yes.
No, this is just a property for like if you look, if you take a look at let me just try. Like this is really just a property that follows from looking at the QAA ansatz and decomposing the gates and layering them.
Okay.
Yeah. It's just meant to be to say, okay, we can somewhat control the depth of the circuit, and this is of course very interesting for like disk term devices, because we can like, for example, this P is also something that we can control. We can say, okay, what happens if we choose P equals 1? What kind of quality do we get?
And your statement is rather like this can be chosen to be like that. Because there's all the like the naive goal is that would be larger, but that's not the point.
Yes. You can like we could choose the P such that it fits to our architecture.
Okay.
So what's the meaning of PV?
P was the level of QAA. This is something that we can choose in advance, and it basically tells us how much we want to discretize our evolution. And so it's known that if you fix the problem instance and you choose P very, very, very large, then you achieve the maximum length. But this would be saying like, okay, if I just go through all the possible solutions, then I will find the maximum solution. Like it's basically the analog of a brute force.
And for P equals 1, you often have like efficient classical simulation.
That's another point. Yeah. So you're trying to like basically you would like to have very good results for P equals 1, but oftentimes this is not possible for very low P.
So P is like how much you optimize?
Exactly. Yeah. Like so you would. Yeah.
Just don't optimize, then it's fine.
Yeah, but then you might need exponentially long time. Like so, this depends on the spectral gap of your Hamiltonian and of your problem instance. Like if the spectral gap vanishes, then you would basically have exponential time evolution, and then, as I've said, at that point you can just brute force. So,
Doesn't D come from factorizing the HG exponential? Like if you have e to the IEHG and then factorize this to get to that speed.
yes, exactly. Like this is where the maximum degree comes.
And then the P comes from, well, so the definition you have P.
What you've chosen.
P, whatever layers.
Exactly what you've chosen in advance. Yeah. Okay. Other questions? Yeah.
Is there a hardness of approximation result for max cut?
Yes, there is. So for max cut in general, there is, I think it's 16/17 or something, and you cannot approximate anything.
So it's known that there's no efficient combinator, but there's for better ratios.
Well, unless P equals
It's a
infinity.
Knabe.
Something like this, yeah. And there's actually, like, if you assume the unique games conjecture, then there is even a stronger statement, which I will come to. So.
And following up on this, and from the other side, I mean, there's this kind of like low-level convex relaxations that give like polynomial time lower bounds, and like the combinatorial people working in the field don't know these bounds like out of their head. You ask like Pohuta next door, I would say, oh, there's ratio is like.
Yeah.
And can you kind of put the numbers into context, like how these upper and lower bounds?
I was going to talk about this a bit.
So I have a more basic question about the setup. So you said in the beginning it's about getting to the ground state of HG.
Well, here it would be for the maximum state. Yeah.
Or like and minus HG.
Yeah.
So, but this ground state, I mean, since it's a continuous vector, I can just write down identity, and you can also do this for the state or for the Hamiltonian you start with. So it's really about like the evolution itself in between where the computation is done.
Yeah, exactly. Like this evolution might take very long and might be just exponential. Like this is the problem. Obviously, as you said, like these all could be like. Yeah.
And why is it important to start from this other Hamiltonian?
Well, the idea is that for this Hamiltonian, we don't know the ground state space, but for the other Hamiltonian, we do know it, and we can actually easily prepare it, which was this whole plus state. And then we adiabatically evolve from this one, which we can prepare easily, to the one that we actually care about, and then we measure, and then we get some candidate solution.
What's the problem with preparing this ground state of this Hamiltonian?
We don't know.
It's not yet.
Yeah.
Can you give an example of some interesting problem that can be phrased as a max cut problem?
Well, technically, it's
this problem.
Yeah. Yeah. I mean, it's basically just like some benchmarking problem, but I don't know. Like, you mean a real world problem?
Something like that. I don't know.
I don't know. Like, you want to maximize. Like, I don't know if you have people with different characters or something, maximize them. I don't know.
I'm sure Facebook has thought about it.
Exactly. Yeah. Like, yeah. Okay.
I'll ask Superman.
Yeah. Okay. And now, so basically what I've done in all my work, or what we've done in all our work, is we care mostly about so-called approximation ratios, like how good are these approximations. So obviously, like via this trotterization or like not evolving enough, you will not actually get to the ground state, to the perfect solution in polynomial time. So what we care about are approximation ratios. Like if you have some approximation algorithm, then and you have some instance G, then this approximation ratio of this algorithm applied to G would be the expectation values of the, in particular for max cut, of cut size of A applied to G divided by the actual max cut. Now, obviously, we cannot really, like for a specific instance, we cannot really compute this, because otherwise, well, we would compute max cut, and this is NP. So this is not really possible, but you can give some lower bounds on these approximation ratios. And what we were particularly interested in are the worst cases, like the minimum over some channel.
Sorry, this approximation ratio is independent of whether it's a quantum or a classical algorithm.
Correct.
And I presume you want some approximation ratio which is better for a quantum algorithm.
Yeah, you would like, in a perfect world, you would have some quantum algorithm which outperforms the classical algorithms in terms of this approximation ratio. Yeah. Mm-hmm. And so, so for max cut, there is a very famous algorithm, like already implied by Jens, which uses STP, like semi-definite programming, which is called the Guillemot-Williamson algorithm by Alexander. And this algorithm achieves, like on any graph, no matter what it is, it achieves an approximation ratio of roughly 0.8785. So in other words, you apply this algorithm to the max cut problem on some graph, and you will always know, okay, the solution that is output will be within like, so it will have at least 87% of the actual value. You obviously will not know the value itself, but you're guaranteed to have this value. And this is, of course, a very high benchmark. And basically what we were trying to ask in the very beginning, in the very first paper that we talked about.
Sorry, I have a question.
Yeah,
so that statement, is that for any graph?
That's for any graph.
Oh,
yeah, and that's I know it's amazing. Like that's and it's really mind blowing, and it's a very simple algorithm actually, or relatively simple once you know how to solve STPs. Yeah, and so yeah, and in our very first paper, or in our very first steps to analyze QAOA, what we did was actually ask, okay, are there any worst case examples? Like, how does QAOA perform in the worst case for this max cut problem? And we showed that this, if you choose the level of QAOA constant, like independent of the problem size or the problem graph, then you will always find instances for which this the QAOA performs worse than this classical.
Can I ask you a question? I mean, like, I'm not quite sure I understand like what worst case means in the setting, because I mean the QAOA is like an ansatz class, but of course you still have to kind of find a kind of classical optimization over that algorithm. Like,
yes.
So are you saying that no algorithm that with no kind of classical control, like assuming like okay, allowing for exponential classical computational time to find the optimal like knobs for your QAOA, then you say that even given that computation capability, then even then the worst case setting is worse than this.
Yes, that's precisely what I'm saying. So this is a good point. So far I've glossed over this optimization aspect in terms of these angles, like you want to optimize these angles actually. And in fact, it has been shown by some other Kliesch, who is not related with me, that this is actually an NP-hard problem.
It was nice. former student, yeah, Martin.
Okay, yeah, Martin Kliesch, yeah. So they showed that this problem is actually NP complete, so finding these parameters like in the worst case. So we're kind of glossing over this, but we actually show even if you had this capability of finding these optimal parameters, you would always find these examples which are worse than that.
So essentially, it's sort of like for any set of parameters one chooses, you can create some spoof graph on which it performs badly.
Exactly. Yeah, that's pretty much what we're saying.
Like these are not even for constant depth circuits. Like the circuit depth still grows because the depth of the graph can grow itself.
So for our graphs, if you choose, you can choose the graphs deregular actually.
Okay.
Yeah, and then if you choose P, then this is a constant.
Okay.
Yeah.
But it's kind of stronger even if the circuits.
Yeah. And actually, it's not just for constant depth. It's actually it's even allowed to grow logarithmically, and it still doesn't hold. But obviously, like the most interesting cases, just like we've already said, like in the beginning, you choose your P fix, and then you run the algorithm, and then you know, okay, worst case, this you will have some bad examples.
No, but so your result that you talk about now, does it only hold for P constant or also for P logarithm?
It also holds for P logarithmic, or at least it has to grow logarithmic in order to have a chance to surpass the Squamous-Williamson plot.
Okay, this is like a worst case result for graphs, right? Like
Yes.
What about like average case?
This is something that we have. So average case results are notoriously difficult
Yeah,
to
but
achieve.
like, is anything known, or is it just like?
As far as I know, there's not much known about this. Yeah.
Is the hardness result for max cut on the average?
On average, I'm not aware of some, but I don't
I
know.
mean, that would be, I guess, a prerequisite for. I mean, not necessarily.
I mean, the nice thing.
On average, what does that mean? I mean, that means also that
Exactly,
it's
like
defined
what's-
on the probability measure. Like for example, in freestyle itself. I mean, of course, that's NPRs in worst case complexity, like more than by definition. But I mean, there's also like a sub-unsub condition, and there's lots of regimes where you can find a solution in 40 times.
Yes. Like, I mean, what does it even mean? Like, what is the distribution that you have? And so there's worst case. The nice case about worst case is the nice thing is that like it's very well defined. Like everyone knows what worst case means, and you don't have to discuss different distributions.
But are there like families of graphs for which you expect the approximation ratio to be better for CHOA?
Not. Well, not necessarily, not better. Like I personally don't think that there is such a family. In terms of, I mean, this doesn't mean that QAOA is a bad algorithm, but because, for example, like as we've seen, like for regular graphs, this would be a constant circuit depth. Like that alone is already worth something. While in the other algorithm, you have to solve an STP, which is not that computationally easy. But in terms of approximation ratios, I don't think there is. I'm not sure there is a very well behaved.
But to follow up on Joseph's question, I mean, that's an interesting question.
Yeah.
I think even in the kind of the quantum chemistry world, it's kind of interesting to when we discussed this a bit in the group. It's like interesting to like find the sweet spots of where one can even hope quantum variation answers to be good.
Yeah.
Because I mean, in many settings, I mean, of course you can find a quantum answers, but they have to be those for which you can find the nice tensor network answers as well.
Yeah.
Like I mean, the simplest example is like ground states of like one-dimensional gap Hamiltonians at a linear depth quantum circuit. Wonderful. That's the sequential preparation of an MPS, for which I can just run a tensor network algorithm. So and other settings may be difficult for tensor networks, but they may be challenging as well for the quantum answer. So finding these sweet spots is generally interesting, and the question comes up in a different flavor also here.
Yeah. Okay, let me just briefly like write down this example, statement, or so this is from our first paper. So basically, for all degrees greater than or equal than 3, there exists some family. And all these graphs are bipartite and irregular. And we can actually explicitly state this bound. So this alpha GN, Q 2AOAP is less than or equal than 5/6 plus some term, which only depends on the degree. And this term in particular goes to 0 if we choose D large enough. If we choose D go to infinity. And so in other words, worst case wise, we see that the lower bound is, or the upper bound in terms of this approximation ratio is 5/6. And since 5/6 is less than the Grumman-Williamson bound, we have our statement. Like, so just as a reminder. Like that's our statement. And the way we show this, I'm not going to go too much into detail because of time reasons, but the way we show this is via these NLTS constructions. So there is this no low energy trivial states conjecture, which basically states that there are Hamiltonians for which, if we have some product state and some shallow circuit, then any output of this state has some energy bounded away from 0, like some average energy. And we settled this conjecture for very symmetric circuits and input states, so so-called Z2 symmetric, which so the circuits commute with the X tensor N operator, and the product states are just eigenstates of these operators. And in that way, so we show this actually, these abstractions for all such circuits. And what's nice about this is that this holds for any set of angles. So no matter how I choose my angles or how I choose my angles, I will always have such obstructions, and therefore we bypass this need to find the optimal angles.
Can I ask another question? You tell me if I ask too many questions, then I shall. But that's of course super exciting. But like in the past, we've discussed like the quantum PCP theorem in many places. We had a nice reading club on this, and of course, you mentioned this conjecture also featured strongly there. Could you kind of prove idea of having like a ground state and like a setting that commutes with all X Pauli strings? Could that kind of that proof technique be generalized to larger classes settings where this?
That's an interesting question. So the key to using this NLTS result is that our Hamiltonians are simply just the max cut Hamiltonians on certain expander graphs.
I see.
Yeah, and that's how we can we can leverage this into these approximation ratios. The problem is these Hamiltonians, they don't really work for the general NLTS setting. Like they only work for the symmetric setting. But there is actually some new work by Movaha and Hatfield, I think, where they look into this a bit deeper, and they define something called partial Z2 symmetry, where they don't necessarily have this symmetry on all on the entire stator circuit, but only on some.
I see. They use similar techniques to.
They basically generalize these.
Okay, so that's okay. That's what I meant. Okay,
but I'm not sure whether this can be even more generalized. Like these NLTS questions, they're very difficult.
Yeah, I'm aware of this.
Yeah.
Just really to clarify, you show that NLTS on that subclass is not true, or that NLTS with an additional restriction is true?
NLTS with an additional restriction is true. Okay. Yeah, and then. Yeah.
Could you give an intuition for why you can expect to use NLTS to prove a result of this kind?
You mean what? So basically, the idea is that we can lower bound the average energy, like the average output, in terms of some lower constant, because so these graphs that we use, they are expander graphs, and we have some constant which holds for all of it, and this constant is defined in terms of the constant defined to define expander graphs. Like expander graphs are defined in terms of Cheeger constants. And then these Cheeger constants is used in this. So I'm not really super sure, like, or at least I don't remember how we came up with this concretely. But basically, the main thing that we use in terms of symmetry is a certain inequality by Elder and Harrow, which we can then use to lower bound this in terms of this. So I'm not sure if this answers the question in terms of intuition, but I would be happy to discuss this later, like maybe reconnect.
Okay, cool.
Yeah.
This result related to the fact that for this log vector circuit, the QA answers cannot see the whole.
Yes, yes, yeah, that's basically yeah, that's precisely it. Like, so very good point. Like, so this QA ansatz is very local. So we have these local terms, like our Hamiltonian is local, and therefore, if we write the expectation value of the Hamiltonian, then every single term basically just sees a certain environment, like for example, for 3 regular graphs, all these environments look like this.
And is there a doubt? But is this also how the experiment property comes in?
In our results, yes, true. That's how it comes in. So basically, all of these. So for 3 regular graphs, we would only have these properties, these 3 subgraphs, and this is the key weakness of QAOA that we exploit, and which is later exploited even stronger.
So the necessary condition is that the QA answers should be that should have a left large enough such that all the qubits are taken in consideration by.
That would be, yeah, exactly. Then you would have this condition here, and then you could, in theory, see the whole graph. And then you might actually attain the optimum. But then this would obviously be dependent on the problem size. Okay. Yeah.
I want to ask, your Hamiltonian is not the only involved this interaction, so it can be seen as a classical Hamiltonian.
Yes, yes.
So, and we know that classical BCP theorem is a whole. So can you prove again classical BCP theorem for your result, or is your result can be proven by?
Well, we use, I mean, in this inequality that we have, we use quantum circuits. Like, so I don't think.
Yeah, it involves extant.
Yeah. Like you probably cannot leverage this. Yeah. Okay.
Sorry, what's this inequality?
It's by Elder and Harold. Like if you
Was in their NL ETS paper?
yes, exactly. I think it was that one. Do they have several or
No, just one.
Okay, then it's.
I'm trying to understand like the message, because like you said before, it could be, I mean, essentially my question is, do you have a lower bound also? Because it could be like maybe the lower bound is like 0.83, but then I get to have constant circuits and then.
I see, yeah. So that's a good question. Yes, this context is important, that's true. Like for 3 regular graphs, for example, we know that QAOA 1 achieves 0.694, like for 3 regular graphs. Yeah. Just to give a bit of context. And that was already something that people were very happy about, that we have something which is better than just randomly guessing.
This property of seeing the whole graph, I think is not a property of just a property of the QA ansatz itself, because here I think that you are using just the locality of the gates, and these are property that is shared by most of the common used ansatz. For example, also advertigent ansatz. So is it also possible to apply this kind of thought to other kind of answers?
Yes, so this our results actually can be extended to all Z2 symmetric circuits, for example. Like so if our quantum circuit has some symmetry, then we could in theory get these bounds. Or are you asking more about the Hamiltonians?
Okay, the graph that you wrote there.
Yeah.
Okay. Came by just geometric considerations, right? For example,
yes,
you have your
you have these strong connectivity properties.
Yes, and here you are not using the fact that you have this Z2 symmetry. You are just using the geometry of the.
Yeah, so this Z2 symmetry is used in this inequality very heavily. Like,
Okay.
like yeah, just if you look through the paper, like here, we write this all the time, like in terms of like, you need the symmetry to establish, for example, lower bounds on certain outputs, output probabilities. Okay, good. Then, okay, let me continue. So, okay, so this was our main result in there. And actually, this was actually strengthened later by other people, by Ed Farhi and others, where they show that the case is even worse. So there are actually worst case graphs for which, in this setting, the approximation ratio is actually not even better than 1/2, which is the one which you would get if you trivially just guessed.
And for one layer.
Yeah, no. In the p equals O log n set.
Oh,
yeah, I know that's very bad for QAA. But obviously, like you can always argue, okay, if we choose p equals 6, for example, then we would have up to 1 million vertices, which we can work with. And like, okay, then it turns into some discussion. What you would say there. But yeah, so this is not the strongest result anymore. But this is. It still could be used for like Z2 symmetric. Okay, and what we also did in this paper, we defined RQAA, so which stands for recursive, and the goal here is we're trying to basically get rid of this locality. Like so, this locality is the limiting factor. And so how does this work? So in other words, we use the QAA state, the QAA P state, simply to find correlations between certain vertices. Like so, we first compute QAA P state. Then let's call this psi, and I'm going to omit the angles, but this would still be there in terms of angles. Then we compute for any edges the expectation value under the corresponding ZZ operator, in order to basically find the correlations between certain vertices. So and then we would find one for which the absolute value is the biggest one, and basically we would then know, okay, these two vertices are either very correlated or very anti-correlated in terms of this ansatz. And then we would simply contract this edge. And we would not, okay, we would basically write down, is this correlated or anti-correlated? And so contraction, what does this mean? This would mean we just identify these, and we would basically get some one vertex less. And that's the idea. So now we have one vertex less, and then repeat on smaller graph. And we would do this, like we would have smaller graphs, and we would do this until, while the number of vertices is greater than some threshold. Then, once this threshold is reached, we then compute solution by brute force. And then we would reconstruct from this solution on this very small graph using these correlations or anti-correlations that we obtained during our procedure. We would obtain a solution candidate for our whole graph. Okay.
Like, how does it scale with NC? Like, I mean, this brute force doesn't only works.
This works for only very, very small NC.
Right. So
like the idea.
And then, I mean, 0.1 and 2 are quite expensive.
Yes, yes.
So if you,
Of
if you
course.
use n arbitrarily, but n
So-
stays constant, it will always explode.
Of course. So first of all, like this is more of a heuristic algorithm. Like it's more meant to be okay. Let's try. And actually, like we do give some analysis in our paper for some very simple graphs. But in general, like this is very complicated to analyze. One reason for this is, for example, that if you look here, like if we identify these two vertices here, this would be some subgraph of a 3 regular graph, but here we would have something 4 regular. So the regularity of the graph could increase and will probably increase. And therefore, this is incredibly complicated to analyze. So we cannot really hope for provable approximation ratios, except for in the very simplest cases. So it is some sort of heuristic, and of course, just like you said, like this is no longer like this NC obviously has to be small enough such that we can actually perform brute force, for example. But in general, we don't really make a runtime analysis, but obviously, like we basically exchange the shortness of the original QAA ansatz for less locality, because this graph now here in this step looks at all of the graph, and therefore this locality no longer holds, but at some cost.
Which steps are the
Pardon?
Which steps did you say? 1 and 2? Or?
In step 2, we basically look at all the edges, and therefore we look at the entire graph.
Sorry, so can you remind me again what the heuristic
Just the P, like we still have to choose some P, and then we compute the QAA state, and then we compute P.
so that's an evolution with this.
Yeah, exactly.
With both Hamiltons.
With both these Hamiltons.
Also with this. not just
Yes,
with
yes.
I mean, when you look at all the graph, but the correlations, like the correlations inside the actual graph are only there if the corresponding edges are sufficiently close. Otherwise, the correlations inside have not really something to do with it.
Well, the correlations are only there if there is an edge, like close.
I mean, listen first, you have to.
Yeah. So, basically the idea is, okay, these correlations tell us, okay, are they supposed to have different colors or are they supposed to have the same colors?
I think what Alex meant is that in the computation of the expectation value, there will always be some kind of finite range around the edge. Because of the entanglement in this stage, that you don't need to look at all the if you expand in some local basis, you don't need to you can basically chop off this efficiently.
I see. That's true. Also, note that for QAA1, we would actually this is actually simulable, classically simulable in general. And this is actually something. So I'm just gonna say these things here. So so our QAA is something that we analyze in the second paper that I mentioned. So for example, we heuristically take a look at. So first of all, we devise some simulation algorithm for QAA1, and then we heuristically make some random graphs up to 300 qubits. Or qubits in that case for the max 3 cut problem. And then we compare the approximation algorithms between QAA1, RQAA1, and actually the best classical algorithm for the max 3 cut algorithm, max 3 cut problem, which achieves an approximation ratio. So I'm just going to write it down here of 0.83. And we find that for many of these parameters, our QAA actually is capable of outperforming this. Look into the paper for the figures. But this is of course very heuristic. And as I've said, a general analysis of our QAA is just basically impossible because of these reasons that I stated. But still, it's apparently something that people somewhat use.
Sorry, why can't you analyze it?
For example, because if in this contraction step that we use here, the degree of the graph might become larger. And in order to analyze QAOA, one important thing is, or one thing that makes it easier to analyze is if the degree of the graph is constant. Okay, and one other thing that we also show in the second paper is we use the arguments by Farhi to show that this approximation ratio is actually in the worst case 1/2, and we apply it to the max k-cut problem and show that something similar happens there. So for the max k-cut problem, the approximation ratio of like the trivial algorithm is 1 - 1 over k. If you really just randomly assign k colors to it. And we show that there are also certain graph instances for which QAOA cannot exceed this approximation ratio unless it grows logarithmically with the problem size.
Is there any reason why people are so interested in QAOA? I mean, not because the specific choice of the answers, because the specific choice of the answers is realistic, and also with your work, and also with one that you mentioned about five, there are a lot of limitations of QAOA, and I'm wondering why we all focus on these particular answers and maybe don't explore other kind of answers. Or
as you've already seen, like we care about limitations, so you're asking the right person. I'm not really sure, like, to be honest, like why people don't really use other ansatz. Well, this one is very motivated by this quantum adiabatic theorem, and I guess it's very natural to choose this ansatz. One other reason is, and this is something, I guess, something to do with the history of QAOA to a certain extent. Like there was this one combinatorial optimization problem where QAOA actually was found to achieve an approximation ratio which is better than the best classical known algorithm at the time. What happened then was that around 10 people or so, like I think Boas Barak was one of them, they sat together and devised some classical algorithm which then outperformed QAOA on the other hand. So, but at that time, like that was the best algorithm available, like the best quantum algorithm. And from what I understand, this was one of the reasons for the hype, but I wasn't in the field back then, but this might be one type of answer to that. But of course, like like another ansatz might of course be even better, but at least this one is physically motivated. That's how I understand. Okay. Okay, and then I want to briefly talk about what we did in our third paper, which is a bit different. Like the first two papers are very related, I would say. So in our third paper, with Libor Zaha and also Robert König, we use post-processing.
What was first and the second paper?
So the first paper was this obstacle paper, like where we had this NLTS stuff and RQAOA. The second paper was where we took a look at the max k-cut problem and QAOA on it, like how badly it performs in the worst case. How does RQAOA perform on it heuristically? That was the second paper. And in our third paper, we basically look, okay, what can we do with post-processing applied to QAOA?
Can I just ask one quick question about this like stronger Farhi result? I mean, they also use similar arguments, like some type of NLTS statement, or do they have like completely different arguments?
They have a different argument, like completely. Basically, what they're doing is they observe that for random deregular graphs, these environments that I drew there, they all look the same. They all look like a tree, okay. And then they can show certain concentration results in terms of these trees, and that in that case the approximation ratio becomes very bad. And then they see, okay, this also applies to bipartite graphs, and then Yeah, it's a little more complicated, but it's a very elegant argument.
Okay, your max K algorithm works.
And our max K-cal argument works very similar to the far right. Okay, so here we have in our third paper we apply post-processing to QAA, and so what does this mean? Now you might think, okay, we just run QAA, we measure, we get some solution, and then we apply post-processing. But actually, there is something cleverer that we can do, and actually we call these algorithms twisted QAA or twisted algorithms. And so we focus on 3 regular graphs. And there is an interesting algorithm by Feige, Krapinski, and Langberg from 02. And their algorithm achieves an approximation ratio on 3 regular graphs, call it FKL, which is at least 0.924. Which is higher than the Gummans-Williamson algorithm, but of course it only works for 3 regular graphs. And how do they do this? They solve an SDP with some additional constraints. Then they round to obtain a solution or a candidate. And then they apply a greedy post-processing. Now, how does this post-processing work, or what does this look like? Yeah, please.
I'm wondering about the SDP. You need to optimize for some kind of complex set, right? What is the
So basically, what these things are relaxations. So you can write the combinatorial optimization problem in terms of and you say, okay, I only care about binary variables, like for example for max cut. And now what you can ask is, okay, what if I don't care about binary variables but about like intervals, like from 0 to 1, for example. Like this is, or basically you don't only look at 0, 1, but maybe even like the whole unit sphere, if you care about -1 and 1, for example. And these type of SDPs, like they all look at this. So this is a relaxation. Okay. And then you solve these, and then you round them with some technique, and then you obtain a cut. That's how Gummans-Williamson works. That's how also this works. Okay. So yeah, so how does this post-processing work? Like, let's imagine for a second that we have here some vertex, and for 3 regular graphs, well, we have 3 edges, and now let's assume that we have some coloring here. Like these have all been assigned the same color, and now one can see, like simply by going through the cases, that if we switch this here, then the cut size will increase. Always, like it depends. Like either if this is 1 here, then it increases by 3. If this is a 0 here, then it would increase by 1. But it always increases. That's the important part. And then you can do this greedily, and then you would obtain this algorithm. And that's basically our idea. That like we want to apply this to QAA. However, so how do they show this result? So they show this result by noting that the cut size of, so this is the cut, this is the graph, and this is basically the output of the algorithm. The cut size of this output is greater than the cut size of the original cut that we had before the post-processing, plus some improvement term. And this improvement term so this here would be a good triplet. Because like a good triplet is one where we have 3 vertices connected by edges, and they all have been assigned the same color. And they show that the set of all good triplets is triplets, like the cardinality times 1/3, is the improvement that you would get via this post-processing that they use. And this is how they obtain it here. And this here is, of course, very, very simply, you can calculate this very simply. And now, what do we do now? So this here in our QAA picture would be nothing but this observable, right? Like basically our first cut, like where C denotes this cut. And now this here, we can basically write as an observable. What do we have to do? We have to count the number of good triplets. And how would one do that in the quantum realm? We would use this projector here, right? Like this projects onto the space of all good triplets, and then we would have some expected value for this. Okay, and now twisted QAA.
Sorry, is there any reason why this only works for 3 regular graphs?
This can work for a higher bound of graphs.
It can,
Yeah,
and then
yeah.
you have like a 1/k factor.
Yeah. Like for 3 regular ones, it's just the ones. But in principle, this works for actually bounded degree graphs. I don't even think they have to be regular.
And does it translate into the quantum case as well?
This improvement, you mean?
Yeah.
That's this is actually, so this equation here is how we translate this into the quantum realm.
Right. Okay. So it's guaranteed in the classical, you just translate it easily.
Exactly.
Okay.
Yeah. That's basically the key idea. Other questions? Yeah. Okay. So twisted QAA. The idea is now, okay, we could simply run QAA and then do the post-processing, but instead we optimize the angles with respect to this observable here. Because this is actually what we care about. This is our lower bound that we would then obtain from the FKL result. And then we run QAA, and then we perform the post-processing, and then we would obtain some cut. And we, in our paper, so we now actually, for once, are positive about QAA. Like we show some provable lower bounds on the performance of QAA in terms of like for different families of graphs, like for example high girth graphs or also 3 regular graphs, and we see like heuristically for low p, the approximation ratio of our twisted QAA p is roughly the same as the approximation ratio of QAA p plus 1, like 1 level above that.
Low peak with respect to n,
not really just low p, like for up to 5 or 6 or something. Yeah, like this is something that we heuristically see, but we have lower bounds in our paper, like provable lower bounds, but we observe that this is roughly the same. And this is of course very nice because it means that instead of running QAA 4, for example, you could just run QAA 3, now twisted version. You have exactly the same quantum resources, like your circuit is the same. The only thing that changes is your optimization, and you have this post-processing in the end. But of course, like this circuit here is, like this quantum circuit here is of lower depth than this quantum circuit here, because the quantum circuit depth scales with p. So this is quite nice. And
so what I understood earlier is that people think about scaling p with n anyways. Or was this just?
Well, it's necessary for
in your proof that you can incorporate.
What do you mean people care about it?
No, I mean like the idea is okay how people think about using it, and you have something like p scaled with log n or something at least when it's like that. So there I thought it was Anyway, that like in the use cases, you would kind of scale the factorization, the larger your graph is to get enough accuracy.
Yes. So we have to say that, so these other results where it scales with long n, like this is of course not in the NISC setting anymore. Like these are theoretical results just to see, okay, how bad can QAOA get? Like this is not something that you really care about in the NISC era, because for the NISC era, this is actually way more interesting, because like for p equals 2 or 3, like maybe you could implement this.
But it's, to be sure, this STP only run at the end in the post-processing. You're not using this along the way.
What do you mean STP? Or
I mean, when you say they solve STP with constraints.
this is this FKL algorithm. Like this is not sorry, this is not twisted QAOA.
Okay.
Like in twisted QAOA, we literally just run QAOA. We optimize just with respect to different to a different observer.
Okay.
In order to get
so
this.
that part of this. Okay.
Sorry. Yeah. So basically all of this above here, or well, actually above here, this is just the classical FKL, just as just as a motivation.
Okay.
So the statement that you wrote there, is it something that you can prove, or is it something that you observe?
You mean this?
Yeah.
And this is just something that we observed heuristically. Like we can prove the lower bounds, or we can prove the approximation ratios, but we just see, okay, they roughly scale, they roughly add have the same approximation ratio, and it's just a nice catchphrase there. Like we can save one level of QAOA by twisting.
If you say you optimize theta gamma with respect to HG plus delta G, does it mean that HG plus delta G is the actual Hamiltonian in the comma, or does it mean that?
No, the actual Hamiltonian in the QAOA is still just HG. Okay. This one here is just because we care about this approximation ratio lower bound.
And how does optimization work? Like what is optimization routine?
Yeah, as I've said, I kind of gloss over this. Like, I mean, usually what we would use is some sort of gradient descent. Actually, in our max k-cut paper, it turns out that for max 3-cut, even grid search works somewhat good for p equals 1, like in order to obtain the optimal angles. Yeah, what the actual routine is, that's something that other people.
Okay, but you have like this HowQuaaA parameterization, and then you have your loss functions like in terms of h plus delta and
yes,
whatever.
Exactly.
Exactly.
Like we do find some witness angles, which and that's why our approximation ratios they're not necessarily tight; they're only lower bounds because we have these witnesses.
Like in the end, I guess at the end you sample from the state.
Yes.
To kind of get your
we get our cut, and then we apply this post processing.
Okay, then it's going to be the same process.
Yeah.
So the question was, these lower bounds, do they scale with P, or I mean, how do they look?
Well, here we actually get just numbers. Like for example, for
some fixed P.
Yeah, we really just
numbers as ratios, right?
Yeah, like approximation ratios. Like one example for it is, so as I've already said, for 3 regular graphs, normal QAOA has 0.69 or 0.6924, and I think for twisted it's 0.74 or something. So we improved by 5 percentage points. Pardon?
There was P equals 3.
P equals 1 for 3. All of this is for 3 regular graphs.
Yeah.
Okay. Yeah.
I'm wondering how to do a fair comparison with the classical algorithm. For example, naive classical algorithm is just try all the possible bit strings that are to the n for Pascal problem. And for example, in QAA, we need to do, for example, fixed density of the angles. We need to do state operation, and we need to decrease a bit of time in order to compute estimates. Do we need to ensure that the total time of a state evaluation is lower than to the n in order to work out in the all optimization algorithm? Because maybe I don't know what.
You mean basically the complexity would be outsourced to the optimization like that's your fear, or
Yeah, my theory is that, okay, you need to do gradient descent, for example. And for each step of gradient descent, you need to do a lot of state separation in order to take statistics. And my fear is that maybe in order to get to the minimum, you need to do maybe more than children state separation.
Well, that would be something that people using gradient descent like basically have to answer. But yeah, of course, like this is. I mean, all these things like barren plateaus or being caught in local minima or something, like these are all very real dangers when you optimize these cost functions, because this is not convex. This is, yeah, like these are basically the same problems as in, like, for example, machine learning or so. But that's a good point. Like, actually, you would probably have to think about this. But if you really have mixed cut problems which are large enough, then you probably at some point just stop your optimization and try to see whether your QAA ansatz already gives you some good approximation. Yeah.
Fixing the angles, okay. Roughly how many states preparation we need to estimate the expectation value?
It's a good question. Like, so I do know that if we like repeat this m log m, so like if we have m constraints and we repeat this like m log m times, then you are very concentrated around the expected value for QAA itself for fixed angles.
Okay.
But like in terms of like how to find these angles, I'm not sure.
Okay.
No, I don't understand. Like, if you have a fixed state to estimate the expectation value, you need constantly many samples, right? To estimate it to constant precision.
Constant precision.
Like by hefting.
Okay.
No, but that's what.
No?
The epsilon precision is like 1 over epsilon squared. Exactly.
Okay. For epsilon constant.
Yeah, but fine. Yeah, that's true. Yeah.
So, like on paper, I think you care about constants here. On paper, you need to do constantly many state preparations to estimate the Hamiltonian for a given state.
If you're given the problem instance, then yes.
I would think.
Yeah. That's true. Yeah.
Yeah.
Like for a fixed problem instance, like.
Yeah, exactly.
So for I'm not sure about this. Fixing the angles for estimating a single expectation value, do we need 1 over epsilon square or 1 over epsilon square times the difference of the largest given values minus the minimum value?
I think that's fixed for a given problem instance. So like
Yes.
usually you ignore that.
Okay.
Yeah. Yeah, like if we fix some problem instance, then there's just a constant number of shots that we would need in order to estimate like the expectation.
I have heard that this can scale with time, no?
I think the point he's trying to make is that, I mean, if not all the terms in the Hamiltonian for which you can't, I mean, of course, if you could measure the Hamiltonian, then it's like one of the stars, but you have to measure the, like, you can only measure non-commuting terms. So I think this is what like it was scaling with what you call D showed as well.
Yeah.
And then D is like the non-commuting part.
Yeah.
But in theory, all types in the function.
Yeah.
I think the point is that Alexander has already proven harmless results. And if you additionally consider those obstacles, it gets even worse.
Yes, of course. Yeah.
Other than that, if you can't find anything, then it doesn't get better.
Yeah.
Okay. Do you have any other questions or?
Yeah. Then let's thank the speaker again.
Yeah.
That was a wonderful talk. Thanks for this, and also to a great discussion. So we have about infinitely discussions, but in the spirit of Hilbert's Hotel, maybe there's infinite plus one questions.
Yeah.
We have only to move on.
Yeah, we have to move on.
Would you consider using power?
I think it's an interesting like test case for like near-term devices, just to see what is possible. Like there is this other result by Daniel Stück-Franzer, for example, in terms of like real life noise. Like everyone always thinks about QAA in terms of like these NISC devices, but these NISC devices also have noise. Like the motivation is of course, okay, if our computation is short depth, then decoherence doesn't do too much of damage, but they show, okay, this will lead very quickly to something that you can sample from classically already, like some Gibbs states.
Yeah, a good chunk of the group is like very deeply aware of this result. We discussed this a lot, and we have a joint follow-on.
Yes.
Because what you say is like pretty not. I mean, it's not noisy, so that.
Yeah, exactly. Like at no point did we assume any noise or anything. Yeah. So if you ask me honestly, I would say no.
But I mean, to be fair to wow, I mean, there's also, of course, like lots of variants there, and I'm not aware of like a comprehensive study of all these variants. Like people saying that like adding counter diabatic terms will make a big difference.
Yes.
There's lots of different flavors, and like different people of the groups have like their own flavor, and they say they can improve something, but there's not really a comprehensive study of what to do. Right? It might be interesting at some point to kind of see what the potential is of an optimized approach, you know, in a way. This HowQuaaA was just basically first short of like taking adiabatic computing and then making big trotter steps and then hoping for the best.
Yes.
I mean, with all respect.
I'm not offended. So. Yeah.
So can you zoom out a little bit and take what you've learned about the limitations of QAA to find another class of variational ansatz that will not have the same limitations?
Well, to be honest, I focused a lot on QAA, like a lot. So as I've already said, like these limitations that we showed in our very first paper, like you can use them in general for these symmetric circuits. Like QAA is one of these symmetric circuits, I would guess, so this basically says, okay, if you have some ansatz which falls into this regime, then you might in principle also be able to show some limitations. Like maybe these limitations are very weak, but nevertheless, they might still be there. Like you would obviously have to do some more calculations in order to confirm this. Like with other ansatz, as I've said, I'm not a huge expert on these, unfortunately, but
the question would be, if you can really identify where the limitations are into QAA or in ansatz.
Okay.
The question is, can you? I mean, you've already shown two variants of QAA, but like, is there a more radical change you can make, or is there another guideline that you should be using that we should be using to find better ansatz? Like, can you hone down on better ways to find ansatz?
I mean, yeah. So basically, all these like this ansatz here suffers from this locality that I've already described, and also to a certain extent from its uniformity. Like if you have a fixed, like if you have two isomorphic graphs, then their expectation value will be the same. And those are basically the two main things that are also exploited in this proof by Fari and also in our proof. So in other words, those two things are probably things to avoid in any proposal that one would make in terms of variational quantum algorithms. But apart from that, that would definitely be an interesting question.
And can you comment on your intuition on how much of that carries over to like other ansatz in a slightly different sense, namely that what you look at is are basically like classical Hamiltonians, right? I mean, you code the problem into HG and then it's just a easing type, local, but not geometrically local Hamiltonian. But you can also think of non-commutative terms.
Yes.
Right. And then you are in the realm of quantum chemistry, and also like these STP relaxations are perfectly non-commutative analogs. And then you can also think of not approximation ratios, but the analog thereof in the non-commutative setting. So how many of your obstructions would carry over to like quantum chemistry, like VQEs? And is that worth pursuing? Maybe we should
like we definitely use a lot that we use Ising type Hamiltonians. Like this is definitely something that we.
No, you need to actually throughout the talk expand a bit at this, like because it seems like you're very much in the poly Z basis.
Yes, yeah. Exactly. So I would guess they don't translate too much into these other realms, but it might certainly be worthwhile. So when you say non-commutative terms, for example, this might be something that actually like increases the locality of such ansatz states,
which would be good for the quantum case.
It's
in a way,
exactly.
it's like, I mean, QAOA is like the most evil setting, and that you're trying to solve a purely classical problem that's purely diagonal in the poly Z basis with something quantum, and hope that the coherence along the way helps you.
Yeah.
It's not so obvious why that should be the case.
Yeah,
but when the variational manifold that you want to approximate happens to have that coherence already, then it seems like more plausible that a quantum ansatz might be.
Yes. This is definitely something that could help, like just like this possible non-commutative commutativity. So yeah.
So if I get right, the HowQuaaA ansatz, say at exponential depth and small enough angles, should become exact, right?
Because you basically just go through you basically brute force.
Exactly.
Yeah.
And but I mean even just the like without optimization, like then I guess for sufficiently small angles and exponential depth, like you kind of rotate out all the wrong parts, right?
So your question is basically, do I even care about the angles if I go exponentially long? Or?
I mean, this is sort of the preliminary. It's not really do I care about them, but there is some prescription of them that should be kind of right. Like a prescription that one can, for like there are many descriptions that are just as fine and people just use them.
That might
just
probably be true.
Adiabatic evolution.
Yes. Yeah.
And
like basically these angles are the amount of time that you involve them, and if you're small angles, probably doesn't really.
Error and then should be fine.
Yes.
Now, so this means in exponential depth you get an approximation factor of 0.999.
Yeah.
And so I wonder, like, what is the iteration of where is the transition between like being bad in terms of 5/6 or whatever, and being at least better than the classical algorithms? Like, is this, can you expect this to be just in the exponential or eventually already in the linear or the non-linear?
I would say like all of our restrictions really are just in the logarithmic setting. So of course, just like you said, the linear setting might, for example, be interesting in terms of seeing whether this still holds. So all of these, so far, all of these results have been in terms of logarithmic. So I would assume that a linear growth of P with the problem size, I think this might already do the trick in terms of like
At least as good as classical.
Yeah. But don't quote me on that. No. Like
I mean, in the end, one can always be with any that as good as classical.
Exactly.
Say, okay, I do my optimization while I just sneak in the classical thing and then I'm done.
Yeah.
So, but like without doing such nasty tricks.
Yeah. I would probably guess linear, but that's actually an interesting question to look at. Yeah. But like all of these logarithmic things, like they all look at this locality, which is a logarithmic bound. Like once you're logarithmic, you see the whole graph. Like
it's essentially the idea that when you have a kind of triple, you kind of, if you sample from something and it corresponds to trivial state and you need some energy, and then you use the energy as thing to say, okay, then it's at best this good.
Yeah.
So sorry, just going back to the middle of your talk. Do different NP-complete problems have different approximation ratios?
Yes,
or-
yes. There's a very rich theory of approximation.
Okay.
Not all I know to be hard to approximate also.
That's the next thing. Yeah. Like for example, the knapsack problem. You can actually arbitrarily approximate this.
I see. So was there any like practical motivation for why you chose max cut? Like, in terms of like approximation ratios, or was
well,
this
we
like an accident with history?
we didn't really choose max cut. Like max cut was just what like all these early QAA papers looked at.
But do you think there might be some problems for?
So
Like, do you think like the approximation ratio has anything to do with whether or not qual can perform better for a given problem?
I do think similar limitations hold for all. I guess you can show limitations in general for any NP-complete problem of this. I would say so, but again, don't quote me on that. But it's I would not say that one technique, like for example here, our 5/6 ratio, like I mean, it's nice that this is less than Gomez-Williams, but maybe for some other NP-complete problem, you would get some obstruction, but this obstruction is not strong enough to rule out that it's better than the classical one. Okay. Like this would always be something that you have to basically compute for your problem at hand. But I would guess that you can always like this locality is always the problem. Like and I guess you will always have some sort of problem there for any NP-complete problem, which can be written in terms of local Hamiltonians.
Yeah, maybe because in the light of time, so maybe we have the last question. We can just continue asking questions, but we can move to a more informal.
Of course.
Maybe the last question.
Yeah, and so when I see the answer, I mean, I'm not at all into the literature or anything of the QA, but if I see the answer, it seems natural to me to apply post-processing of some kind, because
yes.
the answer is just okay, unitary evolution and
yes.
Right? So so first question would be, why did you choose this particular way of post-processing? So it's kind of not changing the quantum part, and then just in the end. And like, because yeah, is there some, or do you think there's some scope for, I don't think about like an interleaved architecture of
the topic.
Okay. Like an interleaved architecture where you have this kind of QRA steps, but then you do standardized measurements. And
okay. I guess the second question we can maybe discuss in private. Like I can and relatively quickly answer the first one. So first of all, we don't only look at this, we also look at some other post-processing procedure, which is called HLZ by Halperin, Liebman, and Zwick. And their approximation ratio is slightly better. Why did we actually care about this? Because of this result. Because of this, because we can somehow quantify or like this improvement via some very easily calculable thing. And in particular, we can cast it in terms of like a new Hamiltonian. Like that was the main idea why we looked at these ones. In principle, you can use post-processing however you want, but maybe you don't have like these types of lower bounds for the approximation ratio. But this was our motivation to look at those.
Thank you.
Wonderful. Yeah, thanks for being so patient with us.
No problem.
That was great, and yeah, thanks everyone.